Right now, a cloud of solar plasma is crossing the distance between the Sun and you. It left the Sun on the 27th of July, and it is not one cloud. Two eruptions are chasing each other, and the faster one is expected to swallow the slower. Forecasters have a storm watch running for the 29th, the 30th, and the 31st of July. So here is the question that everything else in the next 2 hours depends upon. Which way is the magnetic field inside that merged cloud pointing when it reaches Earth? Nobody alive can answer that yet, and that single unknown decides what reaches the ground. Subscribe now and tell me in the comments where you are watching from tonight. The answer arrives about 15 minutes before the storm itself does, and not 1 second earlier. Let's get into it, starting with the document that almost nobody actually read. Part 1. The warning that was written to be misread. The Space Weather Prediction Center issues 3 tiers of product, and the difference between them matters. A watch means conditions are favourable for a storm to develop. A warning means a storm is imminent or already expected within hours. An alert means it is happening now, measured, confirmed and in progress. On the 27th of July, the agency issued watches rather than warnings. Watches in the plural, covering 3 consecutive days of the calendar. The text of that product deserves close reading because the hedging inside it is deliberate. It states that the brunt of the activity is most likely on the 30th of July. It attributes that timing to additional ejections from the 27th and 28th arriving together. And it puts the expected range at levels 2 through 3 on the geomagnetic scale. 3 words in that product carry the entire weight of the forecast. The first of those words is additional, and it is doing quiet work. That word tells you something has already happened before any of this. On the 24th of July, a filament erupted off the solar surface just after midnight Eastern Time. It came from a position on the disk, designated South 20 East 15. A modest flare accompanied it, rated at C2.4, which is barely worth mentioning. Forecasters modelled the leading edge of that cloud at 794 km per second. The shock front ahead of it was clocked at 827 km per second. In the units most people think in, that is roughly 500 miles every second. The agency's own language described that first cloud as weak and as flanking. It was never aimed at us, and it only clipped us on the 27th. That glancing blow produced minor unsettled conditions and very little else. Hold that word, flanking, because it is about to become important. There is a further wrinkle in that first cloud worth mentioning. Filament eruptions of the kind seen on the 24th behave differently from ordinary flares. A filament is a rope of cooler, denser plasma suspended above the surface. It is held up by the magnetic field beneath it, sometimes for weeks. Seen against the disk, it appears as a dark thread across the surface. Seen at the edge of the Sun, the same structure glows brightly. When the supporting field destabilizes, the whole rope lifts away. Those eruptions often produce very little in the way of X-rays, which means the flare rating attached to them is misleadingly small. A C-class flare sounds trivial beside an M or an X, but the mass leaving the Sun can be entirely comparable. That mismatch is why forecasters do not judge these events by flare class alone. They watch the coronagraph imagery for what physically departed the star. Remember that mismatch, because it applies to the coverage circulating this week. Headlines lead with flare ratings because flare ratings are simple numbers. The number that governs the geomagnetic outcome is not the flare class at all. It is the mass, the speed, the direction, and above all the field orientation. The second word is the model name, and the model is called Wissar-Enlil. The first half describes the background solar wind, the constant stream the Sun exhales in all directions. The second half is a 3-dimensional code named after a Mesopotamian storm god. It takes a cone-shaped cloud and pushes it through that background wind toward Earth. That model is excellent at one specific job and structurally incapable of another. It predicts arrival time within roughly 6 to 10 hours, which is genuinely useful. It cannot predict the magnetic structure inside the cloud, and it never will. The third word is the range itself, expressed as levels 2 through 3. Forecasters do not write ranges out of timidity or professional caution. They write ranges because the outcome depends on a variable nobody will measure until the end. Now let me give you the state of the star that produced all of this. Over recent days, the Earth-facing disk has carried a cluster of numbered active regions. They run from region 4493 through region 4497. The lead producer among them has been region 4494. That region is classified as beta-delta, and the classification is not decoration. It describes a sunspot group where opposite magnetic polarities share a single dark core. The field lines between those polarities are sheared, twisted, and forced together under enormous tension. Beta-delta regions are where the violent flares come from because they store energy they cannot hold. On the 26th of July, region 4494 produced an M3.2 flare. It peaked at 28 minutes past 3 in the afternoon Coordinated Universal Time. That flare triggered a radio blackout across the sunlit hemisphere, rated R1, the mildest category available. Early the next morning, the same region fired again, this time an M1.0. That one peaked at 32 minutes past 2 Universal Time. I want to flag something now rather than later, because it will save you confusion this week. Coverage circulating right now claims a much larger flare on the 29th of July. Specific timestamps are attached, and an X-class rating, and it looks entirely convincing. I could not verify any of it against primary sources. What I can trace is a nearly identical sequence of events from late July of 2024. A cannibal ejection, and a watch issued at exactly the same level as this one. The same 2 meteor showers peaked underneath it on the same calendar dates. That resemblance is a genuine hazard for anyone reporting this. Numbers appear to have migrated across 2 years without anyone noticing the jump. So here is what holds up and what does not. Pin those 2 flares down, because everything else this week is decoration. The verified flares are the M3.2 and the M1.0. Both of them came from region 4494 this week. The verified speed near 800 km per second belongs to the filament eruption of the 24th. The verified watch covers 3 days, with the modelled peak on the 30th. Everything else deserves a question mark until somebody produces the primary data. And that distinction matters enormously, because the severity of Thursday depends on one interaction. It is an interaction between clouds that we can only ever partly see. That interaction has a name, and it is the reason this storm could exceed its own forecast. Part 2. What happens when one storm eats another? The word circulating in headlines everywhere this week is the word cannibal. It is a real term of art among solar physicists, not tabloid invention. The physics underneath it explains why these particular events keep surprising the people who forecast them. Start with the simple case, where the sun launches one ejection and nothing else. That cloud carries roughly 1 billion tons of plasma threaded through with magnetic field. It expands as it travels and ploughs into the slower solar wind ahead of it. If it moves fast enough, it drives a shockwave out in front. It reaches Earth 1 to 3 days later, depending entirely on how fast it left. Now take the complicated case, which is the one running this week. The sun launches one cloud, then launches a second from roughly the same region a day later. That second cloud is moving significantly faster than the first one was. The second cloud is travelling through territory the first has already swept clear. Less material in the path means less drag, so it holds its speed better. It closes the gap faster than simple arithmetic would ever suggest to you. When it catches the first cloud, it does not pass through it politely. Magnetized plasma does not simply interpenetrate other magnetized plasma and continue onward. The two structures compress against each other along their meeting surface. Density rises sharply inside that compression zone, and magnetic field strength rises with it. Both of these clouds are, in structure, twisted tubes of magnetic field called flux ropes. When they meet, those ropes deform, sometimes merge, and sometimes reconnect with each other. What eventually reaches Earth is not two clouds at all. It is one merged structure that researchers call complex ejector. Picture two waves travelling down a long and narrow water channel together. A fast wave overtaking a slow one does not glide through it and continue unchanged. The two stack into a single wave taller than either was alone. For a moment, the water ahead is pushed harder than either wave could push by itself. That stacking is exactly why cannibal events punch above their listed weight. Storm strength scales with the product of two separate quantities, and only two. One is the speed of the solar wind hitting us. The other is the southward component of the magnetic field it carries. Compression amplifies that field, so it amplifies the storm even when the speed barely changes. Stay with me, because there is a second consequence, and it is worse than the first. A single clean flux rope has a coherent orientation you can sometimes reason about. If you study the source region carefully, you can sometimes guess its orientation. That guess is unreliable, but it is better than nothing at all. A merged structure destroys that coherence completely, and it never recovers it. The interaction scrambles the internal field, which can now rotate, fold, and reconnect with itself in transit. It produces sequences that no model anticipated and no observer can see coming. So the merger makes the storm potentially stronger and simultaneously makes it less predictable. Those two properties arriving together are why forecasters publish ranges instead of numbers. There is direct precedent for the overshoot, and it is recent. On the 4th of July this year, an event exceeded its predicted level by 2 full categories. For interacting ejector, that is not an unusual failure at all. It is close to characteristic behaviour for this particular class of event, which leaves an obvious objection sitting on the table, and I would raise it myself. If we can watch these clouds leave the sun, why can we not see inside them? The answer has nothing at all to do with the quality of our instruments. It is about geometry, and it puts us in the worst possible place to be standing. Part 3. Why we can only watch it come head-on. The sun's visible disk is roughly 1,000,000 times brighter than the faint atmosphere surrounding it. To watch an ejection leave the star, you first have to block the star itself. The instrument that performs this trick is called a coronagraph. It places a physical occulting disk inside the optical path of the telescope. That disk creates an artificial eclipse permanently inside the instrument. What remains is the corona and any material moving outward through it. That material becomes visible because sunlight scatters off the free electrons inside it. You are not watching the cloud glow, you are watching it reflect sunlight. For 3 decades, the workhorse instrument has been LASCO aboard the Solar and Heliospheric Observatory. That mission is a joint venture of the European Space Agency and NASA, launched in 1995. It was designed for 2 years of operation, and it is still returning data now. There are newer eyes watching the corona as well, in 2 other places. A compact coronagraph flies aboard the GOES 19 satellite in geostationary orbit. Another flies much further out, and I will come back to that one shortly. Here is the geometry problem, and it is not solvable from where we sit. Every one of those instruments sits essentially on the line between the Sun and Earth. A cloud aimed directly at us is therefore aimed directly at the camera. You never see it in profile, only expanding outward from behind the occulting disk. It grows into a faint ring that eventually encircles the entire field of view. Forecasters call that a halo event, and a complete halo means something is coming for you. But a halo tells you remarkably little about how fast anything is moving. Everything you measure is motion across the sky, perpendicular to your line of sight. The motion along your line of sight determines when it arrives, and that component is invisible. You are watching a projection of the thing, not the thing itself. Try judging the speed of an oncoming car by looking at it straight through a windscreen. You know something is approaching, and you know roughly how large it is. Estimating how fast it closes is a completely different problem, and you will be wrong. That is why arrival forecasts carry 6 to 10 hours of uncertainty on a journey lasting days. A forecast can be half a day out without anybody having made a mistake. Hold that image of the oncoming car, because it explains a decision made in Europe. There is a partial solution to this, and it has already proven itself once. Place a spacecraft off to one side at a different point along Earth's orbit. From there, the same cloud appears in profile rather than head-on. Speed becomes directly measurable, and internal structure becomes partly visible. NASA flew exactly that experiment, launching 2 spacecraft in 2006. They were named Stereo A and Stereo B, and they drifted slowly ahead of and behind Earth. Stereo A is the spacecraft that flew through the superstorm of July 2012. That storm missed Earth entirely, and we measured it anyway, in full detail. The European Space Agency has designed a mission to make that side view permanent. It is called Vigil, and it will sit at the 5th Lagrange point in Earth's orbit. That position trails 60 degrees behind us as we travel around the Sun. From there, Vigil will watch active regions rotate toward Earth before they ever face us. It will see ejections in profile instead of head-on, which changes the forecasting problem entirely. Vigil is currently planned for launch sometime around the year 2031, which means that for the next several years, including this exact week, the limitation stands. We watch these clouds come at us head-on, from directly inside the line of fire. But there is one measurement we can still make, and only at the last moment. It happens at one specific point in space, and that single point decides everything. The instrument reading it there has been fully operational for less than 2 months. Part 4. The 15 minutes nobody can extend. There is a number I want you to carry through everything that follows tonight. That number is 15 minutes, and it does not stretch for anybody. That is roughly how much confirmed warning our species gets before a solar cloud strikes. 2 days is the estimate we work from, and 15 minutes is the confirmation. Roughly 1.5 million kilometers sunward of Earth lies the first Lagrange point. It is a gravitational balance point between the pull of the Sun and our own. A spacecraft placed there orbits the Sun at exactly the same rate we do. It holds station permanently between us and the star, like a buoy anchored upstream. Everything upstream of that buoy is inference, and everything measured at it is fact. A spacecraft parked there flies through the incoming cloud shortly before Earth does. It measures the speed of the solar wind and the density of the material. It measures the strength of the magnetic field, broken into separate directional components. The component that decides everything is the north to south component, written as BZ. Now, why should north or south matter so enormously to a planet? Earth generates its own magnetic field inside a convecting core of liquid iron. Out in space, at the front of our magnetic cavity, that field points northward. When the incoming cloud carries a northward field as well, the two fields press against each other. They repel, exactly like two magnets held pole to matching pole. The solar wind then slides around the outside of our magnetosphere and continues on its way. The shield holds, the cavity compresses slightly, and almost nothing else happens. When the incoming cloud carries a southward field, the geometry inverts completely. Two anti-parallel magnetic fields pressed together do something specific and dramatic. They reconnect, meaning the field lines break and reattach across the boundary between them. In doing that, they open a door that is normally latched shut. Solar wind energy that should have been deflected now pours directly into the system. Earth's closed field lines get peeled open on the day side and dragged backward over the poles. They pile into the long magnetic tail trailing behind us on the night side. When enough energy accumulates back there, the tail snaps back through reconnection of its own. Charged particles are hurled down the field lines into our upper atmosphere. That entire process is a geomagnetic storm, and it is also the Aurora. The physicist James Dungy worked this cycle out during the 1950s. It remains the backbone of everything we understand about the Sun and Earth. Southward field opens the door, and Northward field keeps the latch closed. Hold that door in your mind, because I will come back to it repeatedly. So the entire question of Thursday reduces to one property of one cloud: whether the field inside it points southward, for how long, and how strongly. Researchers use a rough threshold of about -10 nanotesla, sustained beyond 3 hours. Cross that line and you have a genuine storm on your hands. And we cannot see it coming, not from here, not with any instrument we own. The magnetic orientation of plasma at that distance cannot be photographed. You have to be physically inside the cloud, holding a magnetometer. There is one more question worth settling before we leave the mechanism. Why can nobody simply model the magnetic orientation from the source region? The Sun is observed continuously in many wavelengths by several spacecraft. Surely the twist of the flux rope is measurable before it leaves. The answer is that we measure the field at the surface reasonably well. Instruments called magnetographs map the magnetic field across the visible disk daily, but the eruption happens above that surface, in the corona itself. Measuring the coronal magnetic field directly is an extraordinarily difficult problem. The gas there is thin, hot, and the signal is faint. Techniques exist, and they are improving, and they are not yet operational forecasting tools. So models extrapolate the coronal field upward from the surface measurement. Those extrapolations are genuinely useful, and they carry substantial uncertainty. Then the cloud spends 1 to 3 days travelling through the solar wind. During that journey it expands, rotates, and deforms against the wind ahead. It can be compressed from behind by a fast stream, as described earlier. Every one of those interactions changes the orientation of the internal field. Imagine predicting the final orientation of a leaf dropped from a bridge. You know the leaf, you know the bridge, and you know the river below. You still cannot say which way it faces when it lands downstream. That is the honest state of the forecasting problem today. There is genuine research working towards solving it, and progress is real. Some groups model the flux rope from eruption through arrival numerically. Others use machine learning trained on decades of measured arrivals. Both approaches show promise, and neither is reliable enough for operational use. Which is why the entire global system still rests on one measurement. One magnetometer, 1.5 million kilometers upstream, reading the field directly. Everything else is preparation for a number that has not been measured yet. Which brings me to something that changed recently and that almost nobody reported. For the past decade, that buoy was held by 2 aging spacecraft. The Advanced Composition Explorer launched in 1997 and still operates today. The Deep Space Climate Observatory launched in 2015, built from hardware stored since the 1990s. space weather forecasting for the entire planet ran on equipment decades past its design life. That situation has now changed, and the timing is remarkable. On the 24th of September, 2025, a Falcon 9 lifted off from Kennedy Space Center. It carried NASA's Interstellar Mapping and Acceleration Probe as its primary payload. Riding alongside were the Carruthers Geocorona Observatory and a NOAA spacecraft bound for the same buoy. That NOAA spacecraft reached its station in January of 2026. It has since been renamed Solar 1, and it is watching right now. It carries 4 instruments, and each one matters this week. A solar wind plasma sensor and a suprathermal ion sensor measure the particles. A magnetometer reads the field orientation of whatever eventually arrives there. A compact coronagraph images the corona from a position far outside Earth's orbit. In June of 2026, that coronagraph was declared fully operational. On the 23rd of July, the agency announced the whole observatory was operational. Its imagery began flowing to the public webpage at a 15-minute cadence. That announcement came 6 days before this stormwatch opened. I want to be careful here rather than dramatic, because the distinction matters. Solar One is not experimental hardware flown out there on hope alone. It is a purpose-built operational asset, designed for exactly this job. But operational assets have commissioning periods, and commissioning periods produce surprises. A system with weeks of history does not carry the confidence of one with decades. There is one more thing about that 15-minute figure worth understanding. 15 minutes is what a genuinely fast cloud will give you. A slower cloud might allow closer to an hour of confirmed warning. That window is the entire time available to act on confirmed information. Inside it, a utility can reduce loading on its most vulnerable transmission lines. It can bring reactive power reserves online and cancel maintenance that leaves equipment exposed. Airlines can reroute the flights currently crossing the polar regions. Satellite operators can command spacecraft into safe modes and postpone maneuvers. 15 minutes is enough to accomplish some of that work. It is nowhere near enough to accomplish all of it. Take that number with you, because later I will tell you something that dwarfs it. It concerns how long it takes to replace the single most vulnerable machine in the electrical grid. Setting those two numbers beside each other is the most uncomfortable comparison in this entire field, but none of it makes sense until you understand what the sun actually is. It is not a ball of burning gas, and that misunderstanding hides the whole mechanism. Part 5. The machine that manufactures these things. The sun is not on fire, and it never has been. That single framing, absorbed by most of us as children, blocks everything that follows. The sun is a sphere of plasma, meaning gas so hot that electrons have been stripped away. Plasma conducts electricity, and that one property changes absolutely everything downstream. A conducting fluid in motion generates magnetic fields, and those fields push the fluid around in turn. The sun is a self-sustaining dynamo, and everything violent it does is magnetic in origin. Now add rotation, which is where the trouble genuinely begins. The sun rotates, but not as a solid body would. Its equator completes a single turn in roughly 25 days. Its polar regions take closer to 35 days to do the same. That difference is called differential rotation, and its effects compound without limit. Picture the sun's field at the start of a cycle as clean lines running pole to pole. They resemble the lines of longitude drawn on a globe in a classroom. Now spin the middle of that globe faster than the top and bottom. Those lines are frozen into the conducting plasma, so they get dragged along. After 10 rotations, they are noticeably bent out of shape. After 100, they are wound around the star like thread on a spindle. Every turn stores more energy in the tension of the field itself. Wound magnetic field is not a stable arrangement, and it does not stay wound forever. Buoyant ropes of that field rise through the convective layer and break through the surface. Where a rope breaches, you get two spots, one outgoing and one returning. That is a sunspot pair, and it marks the footprints of a magnetic arch. They appear dark because the intense field suppresses the convection, carrying heat upward there. Less heat arrives, so the region is cooler, so it looks black by contrast. A sunspot lifted out and placed in our night sky would outshine the moon. Solar physicists classify these regions by magnetic complexity using Greek letters. Pay close attention to these 4 letters because one of them is doing everything. An alpha region carries a single dominant polarity and behaves itself. A beta region has a simple pair, positive and negative, cleanly separated. A gamma region has polarities intermixed in ways that defeat any simple dividing line. And a delta region has opposite polarities crushed together inside a single dark core. Delta regions are where the violence lives, and the reason is straightforward. Opposite fields forced into contact and continuously sheared by the plasma beneath cannot hold. They accumulate energy steadily until something inside them finally gives way. Region 4494, the region behind this week's flares, is classified beta-delta. The release mechanism is magnetic reconnection, the same process I described at the door. Field lines under enough stress snap and reconnect into a lower energy arrangement. The difference in energy escapes as heat, as accelerated particles, and as moving plasma. There are 2 distinct outputs from that release, and confusing them is the commonest error made. A solar flare is a burst of electromagnetic radiation, meaning X-rays, ultraviolet, and radio. It travels at the speed of light and arrives here in 8 minutes. It cannot be forecast, only observed, because the warning would arrive with the event. Flares are classified A, B, C, M, and X, each letter 10 times the last. An M3 flare is 3 times stronger than an M1. An X flare is 10 times stronger than any M. What a flare does to Earth is ionize the upper atmosphere on the daylit side. That absorbs high-frequency radio and produces the blackouts mentioned earlier. It matters to aviation and shipping, and it resolves within minutes to hours. A coronal mass ejection is the second output, and it is entirely different. It is matter, physically launched away from the star at enormous speed. Speeds run from about 250 km per second at the slow end. At the extreme end, they exceed 3,000 km per second. Flares and ejections often occur together because they come from the same reconnection event, but not always, and the exceptions are the ones that catch people out. You can have a flare with no ejection following it at all. You can also have an ejection with barely any flare attached. That second case is exactly what happened on the 24th of July this year. A filament lifted off with only a C2.4 flare beside it. Forecasters have a particular nickname reserved for those quiet eruptions. They call them stealth ejections because they arrive without any obvious warning shot. Hold on to that word, stealth, because the record is full of them. So the machine is understood, and the mechanism is not mysterious to anyone. Which raises the question of where we currently sit inside its 11-year rhythm. The answer is the part that almost everyone gets exactly backwards. Part 6. The phase that everyone mistakes for the safe one. The sun's magnetic activity rises and falls on a rhythm of roughly 11 years. At the end of each rhythm, the entire global field reverses its polarity completely. North becomes south, which makes the full magnetic cycle 22 years long. Cycle 25 began in December of 2019 at a very quiet minimum. NASA and NOAA jointly announced in October of 2024 that maximum had arrived. The smoothed sunspot number peaked around the 11th and 12th of that month. That announcement is always made in hindsight, because the smoothing requires a year of data. We are now roughly 21 months past that peak, in the declining phase. And here is the detail that almost everybody has exactly backwards in their head. The declining phase is not the safe part of the cycle at all. Analysis of the long historical record makes this point uncomfortably clear. Among the most disturbed days recorded since 1932, the great majority fell in declining phases. That is roughly 70% of days reaching a planetary index above 7.5. The Halloween storms of 2003 remain the benchmark event of the satellite era. They occurred in the declining phase of cycle 23, not at its maximum. Let me say that again, because it inverts the usual intuition entirely. The most dangerous years are generally not the years with the most sunspots. The reason for that is structural rather than mysterious in any way. At maximum you get the highest sunspot counts and the most frequent flares, but the magnetic field is chaotic then, reorganizing itself, and rarely coherent. During the decline, large coronal holes open across the solar surface. A coronal hole is a region where the field opens directly into space instead of looping back. Solar wind escapes from those regions at substantially elevated speed, so the remaining active regions now launch their ejections into a faster background wind, and a fast stream arriving behind a slower cloud compresses it from behind. That is the same amplification described with the two waves in the channel. It simply arrives by a different route, from behind instead of from within, which means the period we are entering now is not the tail end of anything. Running through roughly the middle of 2027, the record says pay attention. Now this raises a question I get asked constantly, so let me answer it directly. Is the sun itself becoming more active than it used to be? The honest answer has three parts, and only the first one is reassuring. First, the sun is not doing anything anomalous by any historical measure. Cycle 25 has been, by the standards of 3 centuries of observation, moderately strong. It exceeded the predictions made for it, which were pitched low after a weak cycle 24. That overperformance generated coverage suggesting the star was surprising us all. It surprised the forecasters, and it did not surprise the historical record. Multiple ejections in a single week is unremarkable during an active period. Cannibal events are not rare, and a watch at this level happens several times a year. If this feels like more than you remember, two things are happening at once. There genuinely is more activity now than during the deep minimum of 2019, and Aurora photography has exploded across social platforms since 2024. Events that once passed unremarked now generate a full news cycle within hours. Second, and this complicates the reassurance considerably, the sun has not changed. We have changed instead, and we have changed extraordinarily fast. In 1989, when an entire Canadian province went dark, satellite navigation barely existed. Full civilian capability did not arrive anywhere until 1995. There was no precision agriculture and no synchronized measurement network on the grid. There were a few hundred active satellites in orbit around the planet. Today there are thousands of active satellites, the large majority in low orbit. That is precisely the altitude band where storm-driven atmospheric drag operates. One company's constellation alone accounts for most active spacecraft in existence. So when people ask whether these storms are getting worse, the accurate answer is uncomfortable. The storms are the same, and the consequences are growing every single year. That framing changes what you would actually do about the problem. If the star were changing, there would be nothing available to do. Since the exposure is what changes, and we build the exposure, the problem is tractable. Third, and this is the part I cannot resolve for you tonight, we have been measuring this properly for an extraordinarily short time. Continuous ground-based magnetic observations begin in the middle of the 19th century. Direct solar wind measurements begin in the 1960s with the first probes. Continuous coronagraph imaging begins in 1995, which is inside living memory. That is a sample of decades, set against a star 4.5 billion years old. Weigh that sample size carefully, because every risk estimate rests upon it. Extreme events are by definition rare, and rare events in short samples are poorly constrained. We have essentially one confirmed extreme event in the instrumental era. It occurred in 1859, before there was much instrumentation to speak of. Everything we believe about the frequency of such events is extrapolation from a very thin tail. There is one line of evidence that reaches much further back than instruments. Cosmic ray events leave chemical signatures in the atmosphere that get locked away. Tree rings capture them as carbon-14, and ice cores capture them as beryllium-10. Several extreme events have been identified this way across the last few thousand years. One of them, around the year 774 of the Common Era, stands out badly. It appears to have been substantially larger than anything in the instrumental record. The mechanism producing those particular spikes is still debated among researchers, but their existence carries an implication that is difficult to set aside. The event of 1859, which we treat as our benchmark worst case, may not be. That is the most honest answer the available data allows anybody to give. So the star is normal, our exposure is unprecedented, and our sample is far too small, which means the only remaining question is what a storm actually does when it arrives. And to answer that, you need to understand that Earth's shield has holes in it by design. Part 7. The shield that is wide open at both poles. Most illustrations of Earth's magnetosphere do the subject a genuine disservice. They show a neat teardrop shape, a tidy bubble, an obvious and continuous barrier. The reality is messier, and the mess is precisely where the danger lives. Earth's magnetic field is generated in the outer core, where liquid iron convects and rotates. At the surface, that field is what moves a compass needle in your hand. Out in space, it carves a cavity into the oncoming solar wind. That cavity is not remotely symmetric, and its shape changes constantly. On the sunward side, the solar wind compresses it hard. The boundary sits around 10 Earth radii out, roughly 64,000 kilometers away. It moves inward and outward continuously with changing solar wind pressure. Ahead of that boundary sits a bow shock, where the supersonic wind abruptly slows. It is the exact analogue of the shockwave standing ahead of a supersonic aircraft. On the night side, the field is stretched into a tail of enormous length. That tail extends well past the orbit of the Moon, hundreds of Earth radii downstream. Now here is the part the illustrations leave out entirely. The polar regions of that cavity are standing wide open. Field lines there do not close back on themselves near Earth at all. They stream away into the tail and connect to the wider solar system, which means the poles are not protected by the closed-loop geometry that shields the equator. They function instead as a pair of permanently open funnels. Any charged particle that lands on those field lines rides straight down. That is why Aurora forms in ovals around each magnetic pole rather than uniformly. It is also why a storm expands those ovals southward, rather than creating light somewhere new. The oval was always there, and the storm simply makes it larger and pushes it down. Picture the magnetosphere as a tent pitched in a strong wind. The windward wall bows inward, the fabric streams out behind, and the two smoke holes stay open. Nothing about the tent stops what comes down through the smoke holes. Hold that tent, because I will return to what comes through those holes. The sequence during an actual storm runs like this, step by step. The cloud arrives, and if its field points southward, dayside reconnection begins immediately. Our closed field lines are peeled open at the nose of the magnetosphere. The flowing solar wind drags them backward over the poles into the tail. Energy and magnetic flux accumulate back there under increasing tension. Beyond a threshold, the stretched tail reconnects across itself and snaps back toward Earth. Plasma is flung sunward at extremely high speed by that snapping motion. Some of that plasma is injected into a donut-shaped region encircling the planet. That region is called the ring current, and it is genuinely a current. Ions drift one way around it, while electrons drift the other way. The net circulating current generates its own magnetic field, opposing Earth's own. That opposition is measurable from the ground, and it is how we rate storms. The index derived from equatorial magnetometers is called dist, measured in nanotesla. Quiet conditions sit close to zero on that particular scale. Moderate storms reach -50 to -100 nanotesla. Intense storms push past -200, and the great events go far below that. Meanwhile, particles precipitating along the open polar field lines strike the upper atmosphere. They arrive at altitudes between roughly 80 and 300 kilometers above your head. Each collision excites the atoms and molecules waiting up there. The colors are pure chemistry rather than temperature, which surprises most people. Atomic oxygen, excited and left undisturbed long enough, emits at 557 nanometers. That is the familiar green, produced mostly between 100 and 150 kilometers. Higher up, above 200 kilometers, collisions become rare enough for a slower transition. There, atomic oxygen emits at 630 nanometers, which reads as deep red. Molecular nitrogen produces the blues and purples visible lower down in the curtain, and in the same region of the atmosphere, at almost identical altitudes, something else happens. Between 80 and 120 kilometers is exactly where meteors burn up. Keep that overlap in mind, because both things arrive on the same night this week. Before we reach the ground, there is a second scale nobody quotes at you. The geomagnetic scale is not the only one the agency publishes. There are 3 scales running in parallel, describing 3 different hazards. The letter G covers geomagnetic storms, which is what we have discussed. The letter R covers radio blackouts, driven by the flare itself. That is the 8-minute effect, arriving at the speed of light. And the letter S covers solar radiation storms, which almost nobody mentions. An S-scale event is a flood of energetic protons accelerated by the eruption. Those particles do not wait 1 to 3 days like the cloud does. They spiral along the interplanetary magnetic field and arrive within tens of minutes. That field does not run in a straight line between here and the Sun. The Sun rotates while continuously emitting solar wind in all directions. Each parcel of wind travels outward in a straight line from its origin, but the origin keeps rotating, so the stream traces a curve through space. Think of a rotating garden sprinkler throwing water outward as it turns. Every droplet flies straight, and the pattern they form is a spiral. That spiral is named the Parker spiral, after the physicist Eugene Parker. He predicted it in 1958, before any spacecraft had measured it. Spacecraft confirmed it a few years later, exactly as described. Charged particles are bound to those field lines and must follow them, which produces a consequence that surprises people hearing it for the first time. Eruptions on the western side of the Sun connect best to Earth. The spiral from that region happens to intersect our position, so a flare on the western limb, apparently pointing away, can still deliver protons. The cloud misses us entirely while the particles arrive within the hour. This matters directly for the regions producing this week's activity. As those regions rotate westward over the coming days, the cloud risk falls. The particle risk does not fall in the same way at all. Radiation storms are the hazard that reaches spacecraft electronics and human tissue. They are why astronauts shelter and why polar aircrews accumulate dose. They are also why deep space missions need shielded compartments. Keep those 3 letters separate in your head as this week develops. A radio blackout is not a geomagnetic storm, and neither is a radiation storm. All 3 can occur from one eruption, arriving at 3 different times, 8 minutes, then tens of minutes, then 1 to 3 days. That staggered arrival is what makes these events so difficult to communicate. The public hears one word, storm, describing 3 phenomena with different timescales. Agencies publish 3 scales because the underlying hazards genuinely are separate. Follow which letter is being quoted this week, and you will read the situation correctly. There is one more current system you need before we go further. During a storm, intense horizontal currents flow along the auroral oval itself. These are the auroral electrojets, and they can carry millions of amperes. They flow 100 kilometers overhead, they move, and they change strength rapidly. A changing magnetic field induces an electric field in any conductor beneath it. Michael Faraday established that in 1831, and it is taught in every physics course. It is also the entire mechanism by which a storm reaches a transformer. The electrojet above changes, and the ground beneath develops a voltage across it. Anything long and conductive lying on that ground becomes a path for current. That is the complete chain, from the star down to the soil. Which finally brings us to the scale everyone will quote at you this week. The official description of a level 3 storm reads like a list of minor inconveniences, and the historical record contains at least 2 events that make that description look absurd. Part 8. The night 38 satellites fell out of the sky. Let me put the official language beside what has actually happened. The geomagnetic scale runs from level 1 through level 5, mapping onto the planetary index. Level 1 begins at a planetary index of 5, and level 5 arrives at 9. This week's watch sits at level 3, which the agency describes as strong. Here is the official description of what a level 3 storm does. On power systems, voltage corrections may be required at some facilities. False alarms may be triggered on certain protection devices across the network. On spacecraft, surface charging may occur and drag increases on satellites in low orbit. Corrections may be needed for orientation problems on affected spacecraft. On other systems, intermittent satellite navigation and low-frequency navigation problems may occur. High-frequency radio may become intermittent, and Aurora may reach Pennsylvania, Iowa, and Oregon. Read that carefully and notice what the language is actually doing. Voltage corrections may be required, and false alarms may be triggered. Navigation problems may occur intermittently across the affected regions of the world. Drag increases on the satellites flying in the lower orbits. There is nothing there about blackouts, and nothing there about damage. It reads like a list of manageable nuisances written by careful people. That framing is exactly what I want to take apart for the rest of tonight. Set the official wording aside now, and look at what actually happened instead. So let me tell you about the 3rd of February, 2022. That afternoon, a Falcon 9 lifted off from Kennedy Space Center, carrying 49 satellites. They were released into a deliberately low staging orbit before raising themselves higher. The perigee of that orbit was about 210 kilometers. The apogee sat near 350 kilometers above the surface. That company flies this profile on purpose, and the reasoning is genuinely responsible. Deploying low means any satellite failing its checkout will re-enter quickly. It burns up rather than becoming permanent orbital debris for decades. It is a good design decision, and it is exactly what made the next hours expensive. The day before that launch, the Sun had produced a modest ejection. It arrived while the new satellites were still sitting in their staging orbit. The resulting geomagnetic storm was classified at level 1, the lowest category available. That is minor, the bottom rung of the entire scale, and nothing more. It is the kind of event that produces a footnote and a few photographs. Here is what that minor storm actually did to those machines. Energy deposited into the upper atmosphere during a storm heats the gas there. Heated gas expands, which is basic physics anyone can follow. The thermosphere, the layer from 80 to 600 kilometers up, physically puffs outward, which means that at any fixed altitude, the air becomes measurably thicker. Not thick in any ordinary sense, since it remains a hard laboratory vacuum, but drag scales directly with density, and these objects travel at 8 kilometers per second. Analysis by NOAA and the Cooperative Institute for Research in Environmental Sciences quantified it. Density enhancements ran between 50 and 125%. That was measured at altitudes between 200 and 400 kilometers. The company's own statement said onboard measurements showed drag up to 50% higher. That comparison was against previous launches flying the identical profile. The satellites were commanded into a knife-edge orientation to minimize their cross-section. That was the correct procedure, executed properly, and it was not enough. They could not climb out of the thickened air surrounding them. 38 of the 49 re-entered and burned up within days of launch. The estimated financial loss ran as high as $50 million. I want you to feel the weight of that number properly. 38 spacecraft were destroyed by a storm at the very bottom of the scale. It was not level 5, and it was not even level 3. Level 1. The category that appears in no news bulletin anywhere. And the mechanism that killed them was not dramatic in any visible way. There was no arc, no explosion, no failure of any component aboard. The air simply got slightly thicker, and 38 machines could not climb. Now set that beside the orbital environment we have built since 2022. There are far more active satellites now than there were then. The overwhelming majority of them occupy exactly the altitude band affected by drag. Every one of them relies on drag models to predict where it will be tomorrow. Those models assume a thermosphere behaving normally because they were built from normal conditions. During a storm, the models diverge from reality within hours, which means the calculations telling operators whether two objects will collide degrade. Conjunction assessment, as that process is called, becomes noticeably less reliable exactly when everything moves unpredictably. Hold that thought about collisions, because it compounds in a way nothing else here does. Every fragment created by a collision stays in orbit for years. Every fragment must then be tracked, and every fragment threatens something else. The thickening of the air during a storm is temporary and lasts days. The consequences of a collision during that window are not temporary at all. So the official language says drag increases on satellites in low orbit. The record from 2022 says a minor storm destroyed 38 spacecraft. Both statements are true, and only one of them tells you anything useful. But satellites are hardware, and hardware is replaceable given enough money and time. The second case I want to show you involved no hardware failure whatsoever. Nothing broke, nothing burned, nothing fell out of the sky, and the bill still came to more than $500 million. Part 9. The $500 million sky that nobody photographed. On the 10th of May, 2024, the Sun delivered the strongest storm in 2 decades. It has since been named the Gannon storm, in memory of the space physicist Jennifer Gannon. It reached level 5, extreme, the first such event since 2003. The source was active region 3664, an unusually large and complex group. That region produced a sequence of X-class flares over several days. It launched multiple Earth-directed ejections that interacted with each other in transit. The DEAST index bottomed out near -412 nanotesla. The planetary index reached 9, the maximum value twice during the event. Aurora were photographed from Mexico, from Puerto Rico, and from South Africa. Those are latitudes where Aurora simply does not appear in ordinary decades. The pictures were extraordinary, and half the connected world spent that weekend looking up. And while everyone was looking up, something else was happening at ground level. The storm began disrupting satellite navigation at around 2000 hours universal time. The disruption started over North Dakota and spread steadily southward through the night. Total electron content over the American Midwest rose from under 10 units to above 60. That measure describes how much ionized material sits between a satellite and your receiver. Signals crossing that disturbed layer arrive late, scattered, and out of phase. Precision positioning collapses when that happens, and it collapses without any warning. The 10th of May falls in the middle of corn planting season across the Midwest. Now, modern row crop agriculture does not use satellite navigation the way your phone does. It uses a technique called real-time kinematic correction to reach centimeter accuracy. That accuracy is not a convenience in that industry. It is load-bearing. Automated guidance steers the tractor along the row without human correction. Automated section control shuts off individual planter rows crossing a headland. That prevents double planting, which wastes expensive seed and reduces yield. Roughly 72% of United States planted acreage relies on automated guidance. When the correction signal degraded that evening, guidance systems began to fail. Reports from that weekend describe position errors reaching about 70 meters. In the units most people use, that is roughly 230 feet. Some manufacturers' systems refuse to operate at all rather than plant blind. Farmers parked equipment during a planting window, measured in days rather than weeks. Hold that image of a stopped tractor, because it is the whole argument. A research team led by Terry Griffin, an agricultural economist at Kansas State University, quantified it. His co-authors included the space physicists Dolores Knipp, Tamitha Skov, and Scott McIntosh. Their paper was titled Impact of the Gannon Storm on Corn Production Across the Midwestern USA. Their baseline estimate of foregone value came to about $565 million. That figure covered roughly 39,580 affected Midwestern farms. Per farm losses ran between $12,000 and $17,000 each. The Illinois representative farm figure was $16,526. Their upper bound scenario, under less favourable assumptions, reached $1.7 billion. The outage that produced all of this lasted roughly 4 hours. Griffin's own summary of the problem was admirably blunt in its phrasing. He said the timing of the outage, in the middle of May, was a bottleneck in agriculture. And the farms were not the only system under strain that weekend. In orbit, the same storm produced the largest mass manoeuvre ever recorded. Thousands of satellites in low orbit encountered the thickened atmosphere at once. Operators across multiple companies began raising orbits simultaneously to compensate. That had never happened before at anything approaching that scale. The tracking problem that followed was worse than the drag itself. Every object that maneuvers unexpectedly invalidates the predictions made about it. Every object dragged lower than modelled does exactly the same thing. For a period of days, the catalogue of where things were degraded badly. Collision warnings during that window carried far more uncertainty than usual. Operators were choosing whether to burn fuel on manoeuvres they could not verify. Some of those decisions were made on data already known to be stale. Nothing collided that week, and that is genuinely worth stating plainly. But the margin was thinner than the pictures of pink skies suggested. Aboard the International Space Station, the crew took shelter as a precaution. The station orbits inside the magnetosphere, which provides substantial protection at that altitude. But during a severe particle event, crews move into the most shielded modules available That procedure was written after the Halloween storms of 2003. On the ground, grid operators across North America and Europe worked through the night. Utilities reported voltage irregularities and unusual reactive power demand at many locations. Some took generators offline preemptively rather than risk equipment damage. Nothing failed catastrophically anywhere, which is the outcome everyone remembers. But the North American Electric Reliability Corporation logged a long list of anomalies. Those included transformer heating, relay operations, and capacitor bank trips. Each one is minor in isolation, and each one is a symptom. Take that list as the tremor rather than the earthquake. There is one more thing about the Gannon storm worth understanding. Its name was not assigned by any agency using a numbering system. It was named in memory of Jennifer Gannon, a space physicist who died that year. Her work concerned exactly this problem, meaning induced currents and grid vulnerability. The community named the largest storm in 2 decades after her. That detail matters because it tells you how small this field actually is. The number of people worldwide who specialize in geomagnetic hazard is modest. It runs to hundreds rather than thousands across every agency and university combined. That is the entire human capacity assessing a risk measured in trillions of dollars. Now, the Aurora photographs from that weekend deserve one honest caveat. Many of the images circulated from Mexico and the Caribbean were long exposures. The displays at those latitudes were real, and they were mostly red. That red comes from atomic oxygen high above, as described earlier tonight. At extreme distances from the pole, you see only the tallest part of the curtain. The green light lower down sits below your horizon entirely, so the further south you are, the redder and fainter the display becomes, and the more the camera outperforms the human eye watching beside it, which produced a strange effect across social platforms that weekend. Millions of people photographed something considerably more dramatic than what they actually saw. The images were not fake, and the experience was not identical to them. That gap between the recorded event and the witnessed event matters here. It is the same gap running through this entire subject from another direction. The thing that photographs well is not the thing that costs money. The thing that costs money does not photograph at all. Meanwhile, the North American Electric Reliability Corporation reported that the grid fared reasonably well. The lights stayed on across the continent throughout the entire event, and that is the part everybody remembers, which is precisely the problem. The Gannon storm entered public memory as the weekend the sky turned pink. It has not entered public memory as the most expensive 4 hours in modern agriculture. So hold these two numbers together in your head, side by side. 38 satellites destroyed by a storm at level 1 on the scale. $565 million lost during a level 5 where no lights failed. In both cases, the damage arrived through a channel nobody was watching, not the power grid, and not any dramatic visible failure of anything. It came through a quiet technical dependency built into the economy over decades. It arrived so gradually that nobody ever planned for the loss of it. The framework everyone uses to judge these events is whether the lights stayed on. That framework has been wrong for at least 2 decades now. Which raises the obvious question for this particular week in July. Late July is not planting season, so the agricultural exposure is genuinely different. So what is quietly load-bearing right now, at the end of this month? The answer runs through the ground itself, and the ground has form. In 1989, it took an entire province off the map in 92 seconds. Part 10. 92 seconds in the dark. I want to rebuild the 13th of March 1989 as a physical process. Not as a news event, because the news account hides the mechanism entirely. The source was a sunspot region, designated 5395. On the 6th of March, it produced a flare-rated X-15. Over the following days, it launched multiple ejections directly toward Earth, reached a dist of minus 589 nanotesla. That places it among the most intense events of the entire 20th century. At 2:44 in the morning, Eastern Time, the Hydro-Quebec network began failing. Follow this sequence closely, because the speed of it is the entire point. Quebec sits at high geomagnetic latitude, directly beneath the auroral oval during disturbances. It also sits on the Canadian Shield, some of the oldest bedrock anywhere on Earth. That rock is highly resistive, meaning it conducts electricity poorly. Resistive ground is genuinely bad news in this specific context. If the ground conducts poorly, the induced current must find some other path. The path available is the transmission network above it, which conducts superbly by design. The Quebec system is also unusually vulnerable in its physical geometry. Power is generated at James Bay in the far north of the province. It is then carried more than 1,000 kilometers south toward Montreal. Those lines run roughly north to south across resistive terrain. Long conductors aligned with the induced electric field make an excellent receiving antenna. Geomagnetically induced currents began flowing through those lines that night. Those currents are quasi-direct, varying over seconds to minutes rather than cycles. To equipment operating at 60 cycles per second, that behaves effectively as direct current. Transformers are designed for alternating current and for nothing else whatsoever. Superimpose a direct current offset on that alternating waveform, and the magnetic core saturates. It saturates on 1/2 of every single cycle, which engineers call half-cycle saturation. A saturated core stops behaving like a transformer at all. It draws enormous reactive current from the network around it. It generates harmonics, meaning currents at multiples of the fundamental frequency. And it heats internally, in places the cooling system was never designed to reach. Those harmonics are what actually pulled the trigger that night. Protective relays and static VAR compensators stabilize voltage across the network. They detected the distorted waveform arriving and interpreted it as a fault condition. 7 static VAR compensators tripped offline in sequence within moments of each other. With voltage support gone, asymmetry on the 735 kilovolt network reached 15%. 5 separate transmission lines then tripped out almost immediately afterward. Generation capacity of 9,450 megawatts vanished from the system. The entire Quebec grid collapsed in a total of 92 seconds. 6 million people lost their power in the month of March in Quebec. Restoration took roughly 9 hours of work across the whole province. And here is the detail I most want you to keep hold of tonight. At the moment of that collapse, the Deist index sat near minus 138. That is a moderate storm by any reasonable classification of these things. The extreme phase, the minus 589, arrived considerably later. The grid did not fail at the peak of that storm. It failed on the way there, while conditions were still building. Damage was not confined to Canada either, which surprises people who know the story. At the Salem nuclear plant in New Jersey, a generator step-up transformer suffered internal damage. That is one machine, hundreds of kilometers south of the auroral oval, cooked from within. Carry that damaged machine in New Jersey with you through the rest of this. David Bottler of Natural Resources Canada wrote about the event years later. He described March 1989 as the archetypal disturbance for understanding solar-driven blackouts. He is right, and the reason is that every element of the chain is visible. Now let me generalize, because the specifics of Quebec are not universal anywhere. Vulnerability to induced currents depends on 3 separate factors working together. The first factor is geomagnetic latitude, which controls the size of induced fields. Closer to the auroral oval means larger fields driven into the ground. During intense storms, the oval expands southward, which is how New Jersey got hurt. The second factor is ground conductivity, and it varies enormously across continents. Igneous and metamorphic bedrock resist current strongly, as the Canadian Shield does. Sedimentary basins holding groundwater conduct that current far more readily. Coastal regions are the complicated case, and they are the worst case. The boundary between conductive seawater and resistive rock concentrates the electric field. It concentrates it directly along the coastline, where much infrastructure sits. The third factor is network geometry, meaning the shape of the grid itself. Long lines aligned with the induced field are the effective antennas. Lines connecting distant generation to distant load are the classic vulnerable configuration. North America has taken this genuinely seriously since 1989, and it deserves acknowledgement. The North American Electric Reliability Corporation maintains a standard for geomagnetic disturbance. It requires transmission operators to assess the impact on their own systems. They must model the geoelectric fields expected during a defined benchmark event. Where performance is unacceptable, they must implement corrective action plans. In some cases, that means installing neutral blocking devices on vulnerable transformers. Those devices physically prevent quasi-direct current from entering transformer neutrals. Utilities also maintain operating procedures for a warning that arrives in time. On warning, they can reduce loading on the lines most at risk. They can bring reactive reserves online and cancel maintenance leaving equipment out of service. They can reconfigure the network to shorten the effective length of conductors. All of that is real progress. And the same storm today would likely play out differently. Now let me be honest about the limits of that progress. The mitigation depends entirely on warning arriving in usable time, and the warning that tells you the field is southward comes 15 minutes ahead. Some of those actions take longer than 15 minutes across a continental network. The mitigation is also modelled against benchmark events drawn from the historical record. That record, as established earlier tonight, is extremely short indeed. We are extrapolating tail risk from a very small sample of observed storms, and the mitigation protects the network as a system rather than every machine. It does not guarantee the survival of individual transformers at the coasts. Remember that word, transformer, because the next stretch belongs entirely to it. But the grid is not the only long conductor lying across the ground. There are 3 others, and nobody ever intended to build any of them. Part 11. The antenna nobody meant to build. Pipelines are steel tubes running for hundreds or thousands of kilometers underground. They are coated to insulate them from the surrounding soil along their entire length. They are also held at a slightly negative voltage relative to that soil. That deliberate voltage comes from a system called cathodic protection. It exists to stop the pipe from corroding as it sits in wet ground. Electrochemical reactions strip electrons from a sacrificial anode instead of from the pipe. The anode is consumed slowly, and the pipeline survives for decades. During a geomagnetic disturbance, induced voltages appear along the length of the pipe. They can swing the pipe to soil potential well outside its protected range. Where the coating carries a defect, and every long pipeline has defects, current flows. Current crossing directly between steel and soil accelerates corrosion at exactly that point. The consequence is not a dramatic failure during the storm itself. It is accelerated metal loss at specific points, accumulating across the operating life. Operators in the high-latitude regions monitor for this problem continuously. It is another entry in the growing list of consequences that arrive late. Railway signalling is the second case, and it is older than the pipelines. Track circuits use the steel rails themselves as electrical conductors. They detect a train by whether its axles short a circuit through the rails. Induced current in those rails can produce false readings in either direction. A signal can show a train where none exists, or clear a track wrongly. During the storm of May 1921, railway signalling failed across the northeastern United States. Failures were reported across parts of Europe during the same event. A railway signal tower at 57th Street in New York caught fire. That was 1921, when the world carried far less electrical infrastructure than today. Submarine communication cables are the third case, and they are the newest. Long-haul optical cables carry no current in the glass fibre itself, but they carry a high-voltage direct current supply along a copper conductor. That supply powers the optical repeaters spaced along the seabed at intervals. It is referenced to sea earth at both ends of the cable. Induced voltages therefore appear directly across that entire ocean span. During the March 1989 storm, the transatlantic cable then in service recorded this. Its terminals in Newfoundland and England registered a swing of several hundred volts induced across an ocean by lights in the sky. Now, I raise none of these because they are headline risks this week. They are not, and I want that stated plainly rather than implied. I raise them because they show the actual shape of the problem. Nobody designed a global network of long conductors to receive magnetospheric currents. We built pipelines to move gas from fields to cities. We built rails to carry trains and cables to carry data. We built transmission lines to move power from generators to houses. The antenna is an accident, assembled by unrelated industries across a century. Picture a radio receiver built by 1,000 people who never spoke to each other. None of them intended to build an antenna, and none of them checked. Each addition made the receiver slightly larger and slightly more sensitive. That accidental antenna grows every year, and nobody anywhere maintains the total. Sit with that for a moment, because it explains why the risk keeps rising. The storms are not intensifying, as established earlier in the historical record. The receiving array is simply getting bigger every single year that passes. And there is one more thing about it that makes recovery so difficult. The most vulnerable component in the whole arrangement cannot be bought off a shelf. It cannot be bought quickly at any price by anyone at all. Part 12. The clock that no amount of money can speed up. A large power transformer is not really a component in any ordinary sense. It is closer in scale and complexity to a small building. The units that step voltage up at generating stations weigh between 100 and 400 tons. They are filled with tens of thousands of litres of insulating oil. Their cores are built from thousands of thin laminations of specialised steel. That steel is called grain-oriented electrical steel, and the name describes the manufacturing. The crystal structure inside it has been aligned deliberately in one direction. That alignment minimises energy lost as the magnetic field reverses 60 times per second. These machines are typically custom designed for one specific installation and nothing else. Voltage ratings, impedance, cooling configuration, and physical footprint are all specified per site. There is no meaningful inventory of spares waiting in warehouses anywhere. A spare that does not match the specification is not actually a spare. And they cannot be built quickly, no matter what anyone is willing to pay. The United States Department of Energy reported on this to Congress in July of 2024. That report cited 36-month lead times as commonly quoted across the industry. Maximum lead times were reaching as much as 60 months for some units. 60 months is 5 years for one machine ordered today. The North American Electric Reliability Corporation reported similar figures independently. Lead times reached roughly 120 weeks during 2024. Large power transformers were taking as long as 210 weeks to arrive. 210 weeks is 4 years of waiting for one delivery. Industry survey data reported in January of 2026 shows no improvement. Standard power transformers averaged 128 weeks for delivery. Generator step-up transformers averaged 144 weeks for delivery instead. That second category is the exact type damaged at Salem in 1989. Now here is the structural detail that I find genuinely difficult to sit with. Grain-oriented electrical steel is not a commodity you can source from anywhere. Within the United States, there is a single domestic producer of it. That is Cleveland Cliffs. At its Butler Works mill in Butler, Pennsylvania, a sister facility operates in Zanesville, Ohio, supporting the same production. One producer, for the core material inside the machines the entire grid depends upon. I am not presenting that as a scandal, because it is not one. It is the outcome of decades of entirely ordinary industrial economics. A low-margin specialty product consolidated toward its most efficient producer over time. Every individual decision leading to that arrangement was defensible on its own terms. The aggregate result is a supply chain with almost no slack anywhere inside it. Read that sentence twice, because it is the reason recovery timelines look the way they do. So run the scenario now, and not the worst case either, just a bad case, of the kind the record already contains. A severe storm damages transformers across a region in a scattered pattern, say a dozen large units spread across several different utilities and states. The pattern is determined by local geology and network geometry rather than planning. Some of them fail immediately, during the storm or shortly afterward, and some of them do not, which is a genuinely nasty feature of this failure mode. Induced currents degrade insulation through localized overheating inside the windings. Degraded insulation can hold for months or years before it finally lets go. Utilities perform dissolved gas analysis on transformer oil after every major storm. They do that precisely because the damage shows chemically before it shows electrically, which carries an implication that most people have never once considered. The population of transformers energized right now across 2 continents includes damaged units. Nobody can tell you how many, because the damage is invisible until failure. Now those dozen units need replacing, and the replacements are all custom builds. The lead time is 2 to 4 years, as established a moment ago. The queue is shared with every other utility on the planet. Those utilities are already ordering for grid expansion and for load growth. They are ordering for data centers drawing power at unprecedented scale. And they are ordering routine replacements for a fleet averaging 40 years old. The recovery is not limited by money in any meaningful sense. It is not limited by political will or by engineering competence either. It is limited by manufacturing throughput for a specialized product with one domestic steel supplier. There is a second bottleneck underneath the manufacturing one, and it is physical. A large power transformer weighing 300 tons cannot travel on ordinary roads, it cannot cross most bridges, and it cannot turn most corners. Moving one requires a specialized rail car built for exactly this purpose. Those cars are called Schnabel cars, and they grip the load at both ends. The transformer itself becomes a structural member of the vehicle carrying it. There are only a small number of such cars in North America. Each move requires route surveys, bridge load assessments, and utility coordination. Overhead lines must sometimes be lifted, and grade crossings must be reinforced. A single delivery can take weeks of planning before anything moves at all. Picture a piano being carried up a stairwell built for envelopes. The instrument exists, the stairwell exists, and neither was designed for the other. So even a transformer sitting finished in a factory is not immediately available. It must be scheduled onto a rail car that many other utilities also need. The industry has responded to this, and the response deserves credit. Utilities operate shared spare programs, pooling emergency units across many companies. Members contribute to a common inventory they can draw from in a crisis. Those programs are genuinely useful, and they have been used successfully. But they are sized for ordinary failures rather than correlated ones. A shared spare pool works when one utility loses one transformer. It works considerably less well when a dozen utilities lose units simultaneously. Correlated failure is exactly what a severe geomagnetic disturbance produces. The storm does not select its targets randomly across the continent. It hits high latitude, resistive ground, and long north-south lines together. Every utility matching that description is exposed during the same hours, which means the failures, if they come, arrive as a cluster rather than a queue. Now add one more factor to the picture, which is the age of the fleet. The average large power transformer operating in North America is around 40 years old. Many were installed during the construction boom of the 1960s and 70s. Design lives for these machines are typically quoted around 40 years. That does not mean they fail at 40, because many run far longer. It does mean the population is operating deep into its designed lifetime. Insulation degrades slowly with heat and age regardless of storms. So a geomagnetic event does not strike a fresh fleet in good condition. It strikes an aging fleet already carrying accumulated thermal history. Sit with that combination for a moment, because it is the real vulnerability: an aging population of custom machines with no meaningful spare inventory, a manufacturing queue measured in years, and a transport system measured in weeks. One domestic supplier of the core steel, and correlated failure as the threat model. None of those facts is secret, and none is disputed by anybody. They appear in government reports, in industry surveys, and in regulatory filings. They are discussed openly at conferences attended by the people responsible. The information is not hidden anywhere, and it is not hard to find. It simply sits outside the attention of everybody who is not paid to look. Now set the two numbers beside each other, exactly as I promised earlier. 15 minutes of confirmed warning before the storm arrives at the atmosphere, up to 5 years to replace what that storm might destroy. That ratio is the entire problem, expressed as cleanly as it can be. It is also why this hazard differs categorically from most others we plan around. A hurricane gives you days of warning and destroys things rebuilt in months. This gives you minutes of warning and can destroy things taking years. That asymmetry is where every worst-case study in this field originates. In 2008, the United States National Research Council published a study on this. It examined the societal and economic impacts of severe space weather events. Drawing on analysis by John Kappenman, it produced a figure widely quoted since. An extreme event striking modern infrastructure could cost $1 to $2 trillion. That is the estimate for the first year alone after such an event. Full recovery in that study was projected to take 4 to 10 years. Two separate institutions, working independently, landed in the same uncomfortable range. In 2013, Lloyd's of London published an assessment with a research partner. It examined the risk specifically to the North American electrical grid. The estimated cost ranged between $600 billion and $2.6 trillion. 20 to 40 million people would lose power in that scenario. Outage durations range from 16 days at the short end to 2 years. I want to be precise about what those numbers actually are. They are not predictions of anything, and they were never presented as predictions. They are model outputs under worst-case assumptions about how many transformers fail. There is genuine scientific disagreement about whether those assumptions are too pessimistic. Some researchers argue that modern protection would trip the network offline first. The system would save itself by shutting down before the worst damage accumulated. That trades a very long blackout for a much shorter one. That is a real argument, made by serious people, and it may well be correct. But notice the shape of that counter-argument for a moment. The optimistic scenario is that the grid rescues itself by going dark. That is what the good outcome looks like in this field. And none of these figures is a forecast for the 30th of July. A level 3 storm will not damage a dozen large power transformers. I want that stated with complete clarity, because frightening you about the wrong thing helps nobody. What I am establishing is the shape of the risk, so the rest makes sense. Because the exposure is not only transformers, and it has not been for decades. Since 1989, the developed world has built an entirely new dependency. It is invisible, it is universal, and almost nobody has audited it. And that dependency does not run on copper at all, it runs on time. Part 13. The layer that is made entirely of time. Ask anyone what the global positioning system does for them. They will tell you it tells them where they are, which is true. It is also the least important thing that system actually does. What those satellites actually broadcast is not position at all, it is time. Each satellite carries atomic clocks of extraordinary stability aboard it. Each one transmits a signal encoding precisely when that signal left the spacecraft. A receiver on the ground compares arrival times from several satellites at once. From those differences, it solves for its own position on Earth. Position is only a derived quantity, and time is the primary product broadcast, which means any receiver that already knows where it sits can ignore position. A receiver bolted to a building can use the system purely as a clock, and an enormous amount of modern infrastructure now does exactly that. Follow this next step closely, because the recursion in it is unsettling. Consider the electrical grid, since we have spent so long inside it. Across the North American bulk power system sits a network of instruments. They are called phaser measurement units, and they do something specific. Each unit samples the alternating voltage and current at a substation many times per cycle. It reports both the magnitude and the phase angle of that waveform. Phase angle is the genuinely useful part of that measurement. By comparing phase angles at two ends of a transmission corridor, operators see power flow. They can detect oscillations building and identify instability spreading across a continent. But that comparison only works if both measurements were taken at the same instant. Two devices 1,000 kilometers apart must agree on the time. They must agree to roughly 1 microsecond, which the governing standard specifies. Nothing else delivers microsecond time to thousands of unattended sites affordably, so all of them use satellite timing, without exception worth mentioning. The Department of Energy has stated the scale of that deployment. Phasor measurement units have been installed at over 2,500 locations. Those sites sit across the bulk power systems of the nation. An industry initiative describes almost 1,700 production-grade units operating. They cover the United States and Canada, providing near-complete visibility into the system. Now sit for a moment with the recursion buried inside that arrangement. The instrument network that lets operators watch a geomagnetic disturbance develop needs synchronization. That synchronization arrives on satellite signals passing through the ionosphere. And the ionosphere is exactly what the disturbance is currently scrambling. The sensor and the threat are sharing exactly the same channel. I do not want to overstate that, because engineers have thought about it. Modern timing installations often include holdover oscillators for exactly this situation. Those are local clocks maintaining accuracy after the satellite signal degrades. Good installations hold microsecond accuracy for several hours without any satellite input. Better ones, using rubidium standards, hold accuracy considerably longer than that. But holdover buys delay rather than immunity from the problem. It buys time proportional to the quality of the local clock installed. And that quality varies enormously across 2,500 sites. They were installed across 2 decades by different utilities under very different budgets. The grid is not the only sector standing on this foundation either. Financial markets timestamp all of their transactions using satellite timing references. One major exchange times its trades using antennas on its New Jersey server farm. Regulatory requirements for audit trails specify accuracy met, in practice, by satellite. Look at how far outside the grid this dependency has already spread. Cellular networks synchronize their base stations to the same time source. Fifth-generation networks in particular coordinate transmissions across overlapping cells continuously. They share spectrum between uplink and downlink by dividing it in time. Lose that synchronization and adjacent cells begin interfering with each other directly. Data centers, industrial control systems, and emergency dispatch all use the same reference. In 2019, a study for the National Institute of Standards and Technology quantified this. It attempted to price the loss of satellite navigation and timing. For the electric power sector alone, a 30-day outage was estimated. That estimate ranged from $211 million to $338 million. The economy-wide estimate was at least $1 billion every single day. That figure rose to as much as $45 billion under one condition. The condition was that the outage fell during spring planting season. That study was published 5 years before Gannon demonstrated the mechanism in practice. Now, how does a geomagnetic storm actually degrade all of this? There are two mechanisms, and they fail in different ways. The first mechanism is delay, and it is the gentler of the two. Radio signals travel more slowly through ionized plasma than through vacuum. The delay depends on how much ionization sits in the signal path. Receivers correct for it, using models built from ordinary conditions. Dual-frequency receivers can measure and remove much of it directly, but when electron content changes rapidly and unpredictably, the models simply fail. The second mechanism is scintillation, and it is considerably nastier. Irregularities in the ionosphere scatter and refocus the arriving radio wavefront. Signal amplitude and phase then fluctuate rapidly and unpredictably at the receiver. Severe scintillation causes a receiver to lose lock on a satellite entirely. That is not degraded accuracy of any kind, that is the signal disappearing. Scintillation is worst at high latitudes and near the magnetic equator. During disturbed conditions, the auroral zone expands southward across populated regions. The region affected by scintillation expands southward along with it. That is precisely what crossed North Dakota on the 10th of May, 2024, which brings the twist into plain language, assembled now from both directions. The threat everybody pictures is the grid going dark across a continent. That threat is genuine, and it lives at the extreme end of the scale. The threat that has actually materialized repeatedly is entirely different. It is the degradation of an invisible timing layer built underneath the economy. Nobody decided to build that layer, and no sector fully inventories its dependence. The lights stayed on during Gannon, and the bill still reached $500 million. Part 14. The routes that disappear when the radio dies. Late July is the busiest flying period of the year across the Northern Hemisphere, which makes aviation the sector most exposed on the calendar this particular week. Count these 3 channels as they arrive, because they fail one at a time. Aviation is vulnerable to space weather through 3 separate channels. Those channels fail independently of each other, which is what makes the problem awkward. The first channel is communication, and it is the one that grounds routes. Flights crossing above roughly 82 degrees north sit outside satellite communication coverage. The reason is pure geometry rather than any technical shortcoming. Communication satellites in geostationary orbit sit directly above the equator. From very high latitude, those satellites drop to or below the horizon, so polar flights rely on high-frequency radio to stay in contact. That system works by bouncing signals off the ionosphere itself. It is the oldest long-range technique in aviation, and it still works beautifully. Until the ionosphere itself becomes the thing that is malfunctioning. A radio blackout removes that capability across the sunlit hemisphere entirely. Regulations require the ability to communicate with air traffic control. If high-frequency propagation fails, then the route is simply not available. The aircraft itself does not become unsafe in any way. The route becomes legally unusable, which produces exactly the same outcome. The second channel is navigation, and it compounds the first neatly. Near the magnetic poles, compass headings become unreliable as ordinary geometry. Magnetic field lines there run steeply downward rather than horizontally, so polar operations lean more heavily on satellite navigation than anywhere else, which is degraded by exactly the same disturbance affecting the radio. The third channel is radiation dose, and it affects people rather than equipment. At cruise altitude, the atmosphere overhead provides far less shielding than at sea level. Roughly 3/4 of the atmosphere sits below a cruising aircraft. Near the poles, the magnetic field also provides less deflection than elsewhere. The field lines are open there, as established with the tent and its smoke holes. Crews flying polar routes accumulate meaningful occupational dose across a career. A strong solar particle event can deliver in one flight what normally takes months. The standard mitigation for all three problems is the same in shape. Fly lower, which increases fuel burn substantially at those distances. Fly further south instead, which increases the total distance travelled. Or do both at once, which compounds the cost considerably. A rerouted transpolar flight can add an hour or more to the journey. It can force an unplanned fuel stop that was never in the schedule. Direct costs run into tens of thousands of dollars for a single diversion. That figure counts fuel, crew duty limits, and downstream schedule disruption together. Now watch how far that one event reached, across 4 completely different systems. During the Halloween storms of October 2003, carriers rerouted polar flights for days. That same event destroyed the Japanese Earth observation satellite named Midori 2. It disabled an instrument aboard the Mars Odyssey spacecraft at another planet. Astronauts aboard the International Space Station sheltered in the most shielded module available, and in Malmö, Sweden, roughly 50,000 people lost power for about an hour. That last item on the list deserves a moment of attention. Sweden lost power at a high latitude site sitting on resistive ground. It was one city for 1 hour during a storm affecting the entire planet. Everything else on that list happened above the atmosphere, where nobody lives, which tells you where the modern exposure actually concentrated after 1989. Now, late July of 2026 is peak season on the North Atlantic. Transpolar routes between North America and Asia are running near capacity. Schedules across the network have almost no slack built into them. So if this storm delivers at the top of its forecast range, that is the exposure. It is not about blackouts happening anywhere on the continent. It is a sector at maximum utilization losing routes for hours. I want to give you one more sector before moving on, because it is genuinely new. Human spaceflight is more exposed in 2026 than at any point since Apollo. The International Space Station orbits inside the magnetosphere, which provides real protection. Crews there shelter in shielded modules during major particle events, as in 2003, but lunar mission architectures place crews outside that protection entirely. Beyond the magnetosphere, there is no magnetic deflection of solar particles at all. There is only the shielding a vehicle carries with it. A severe particle event during a translunar coast is the scenario planner's fear, and that risk is not theoretical. Which brings me to August of 1972. That month produced a fast, intense storm during the Vietnam War. Its effects on Earth were strange enough that they were classified for decades. I will come back to what happened in the water off Vietnam. What matters here is the timing relative to the Apollo program. Apollo 16 returned to Earth in April of 1972. Apollo 17 then launched in December of that same year. The storm arrived in the gap between them, in early August. Estimates of the dose an astronaut would have received outside the magnetosphere run high. The figures reach several hundred rem, depending on shielding and timing assumptions. That level causes acute radiation sickness, and at the upper end it is worse. The margin between that storm and a crewed mission was 4 months. Hold that margin, because it is the tightest one in this entire record. Nobody planned it that way, and nobody detected it in advance. The Apollo schedule simply happened to place the crews elsewhere that August. That is not a safety system of any description at all. It is luck, recorded afterward and then relabeled as history. So aviation loses routes, spacecraft lose altitude, and crews outside the field lose shielding. Each of those is a real consequence with a documented precedent behind it. None of them involves the lights going out anywhere on Earth. Which finally brings us to the second thing arriving over your head this week. It has nothing whatever to do with the sun at all. It has been travelling for considerably longer, and it comes from something that shattered. Part 15. The other thing arriving on exactly the same night. On the night of the 30th going into the 31st of July, Earth crosses 2 debris streams. Both of them peak on the same night the merged solar cloud is forecast. The first stream produces the shower called the Southern Delta Aquarids. Its radiant, meaning the point the meteors appear to diverge from, sits in Aquarius. It lies near the star scat at a declination of about -16 degrees. That southerly position is why the shower favours the southern hemisphere strongly. The particles enter the atmosphere at about 41 kilometers per second. In more familiar units, that is roughly 90,000 miles per hour. The shower has an unusually long and broad activity period each year. It runs from about the 18th of July into the 21st of August. Peak rates under ideal dark conditions reach perhaps 16 to 25 per hour. The second stream produces the Alpha Capricornids, and it is far weaker. By rate it manages perhaps 5 meteors per hour at its very best. But it carries a reputation completely out of proportion to those numbers. Its meteors are slow, entering at roughly 22 to 25 kilometers per second. And they are frequently spectacular, because slow meteors burn long and bright. This is a fireball shower rather than a counting shower. A single Alpha Capricornid can outweigh an hour of anything else. Now here is what turns this from a listing into a story. The moon is full on the 29th of July, 2026. It reaches full at 36 minutes past 2 in the afternoon, universal time. On the peak nights, it will be about 98% illuminated, and it will be above the horizon for essentially the entire night. So on the one night when 2 showers peak simultaneously, the sky is flooded. It is flooded by moonlight bright enough to cast shadows on the ground. The faint Delta Aquarids will be almost entirely invisible from anywhere. Only the brightest Alpha Capricornid fireballs will punch through that glare. And any Aurora will compete against a background sky several times brighter than normal. 2 uncommon events arriving together under conditions that conceal both of them. I find that genuinely striking, and it deserves more than a passing mention. The sky this week is full of things you will not be able to see. If you intend to go outside anyway, and I think you should, be practical about it. These next few habits are worth more than any equipment you could buy. Put the moon behind something solid, like a building or a tree line or a hill. Direct moonlight in your field of view destroys your dark adaptation completely. And dark adaptation is most of what separates seeing a fireball from missing one. Your eyes need 20 to 30 minutes to adapt properly to darkness. They need about 1 second of a phone screen to undo all of it, face away from the radiant rather than directly toward it. Meteors near the radiant appear foreshortened, as short stubby streaks. That happens because they are coming almost straight toward your position. The long dramatic trails appear 30 to 60 degrees away from the radiant. The best hours are after local midnight, and the reason is orbital rather than atmospheric. Before midnight you sit on the trailing side of the planet. Meteors have to catch up with you from behind, which reduces both rate and speed. After midnight you have rotated onto the leading side of Earth. Now you are running into the stream head-on, rather than being overtaken. The rates roughly double, and the meteors arrive faster and brighter. For the Aurora, if you sit at a plausible latitude, 1 extra point matters. Modern phone cameras on a several-second exposure detect Aurora your eye reads as grey. That is not the camera inventing anything, and it is worth understanding. Human colour vision fails at low light because cone cells need many photons. Rod cells handle dim light, and rods cannot distinguish colour at all. So a genuine red aurora can register to you as a colourless pale glow. The sensor meanwhile records it as deep crimson without any difficulty. If you see an unexplained pale arc to the north, photograph it before dismissing it. There is one further point about the moon that is worth knowing. A full moon reaching 98% illumination raises the sky brightness enormously. The effect is not a simple doubling of the background. A bright moon can raise sky brightness by a factor of 10 or more, which means the faintest meteors are not merely harder to see. They become physically undetectable to the human eye from any location. Meteor counts published for showers assume a completely dark sky. That standard is called the zenithal hourly rate, and it is idealized. It assumes the radiant directly overhead and a limiting magnitude of 6.5. Almost nobody anywhere actually observes under those conditions in practice. Under a full moon, realistic counts drop to a small fraction of the quoted rate. Under ordinary suburban light pollution, the counts drop further still. So the honest expectation for 1 hour outside on Thursday is modest. Perhaps 2 or 3 meteors, and one of them possibly worth remembering. If you want the dark sky version of this shower, that window has closed. The better mornings ran from roughly the 20th to the 24th of July. The moon was still filling out then, and it set before dawn. Those mornings are gone for this year, and they return next July. But the Delta Aquarids remain weekly active well into August. By the second week the moon is out of the way entirely, and the Perseids ramp toward their peak on the 12th and 13th. In 2026, the Perseid peak falls under a genuinely dark sky. There is something else happening on that same date, and it is rare. On the 12th of August, the moon's shadow crosses Arctic Russia and Greenland. It falls across western Iceland and northern Spain near sunset. That is a total solar eclipse. The first over mainland Europe since 1999. It is the first over mainland Spain since 1905. Maximum totality lasts 2 minutes and 18 seconds off the Icelandic coast. So in 2 weeks, Europe gets totality and the world gets meteors, both on the same night under a dark sky, which is exactly the opposite of Thursday. Mark that date, because it is the inverse of everything this week represents. Now let me tell you about the object behind the Delta Aquarids. It is one of the strangest things in the inner solar system. The suspected parent is a comet designated 96P Mach-holes. It was discovered on the 12th of May, 1986, by Donald Mach-holes. He was an amateur astronomer observing from California with his own equipment. I say suspected deliberately, and the hedge is not mine alone. The International Meteor Organization, the American Meteor Society, and NASA all hedge on this. The dynamical association is suggestive, and it is not proven. So when you see confident claims this week, understand the honest version carries a question mark. Here is what makes that object genuinely remarkable regardless of the uncertainty. Its nucleus has an estimated radius of about 3.4 kilometers. That work was published in the Astronomical Journal in 2019. It gives a diameter somewhere near 6.4 kilometers across. The object rotates about once every 4.1 hours. It is elongated, with an axial ratio of at least 1.6. Its orbit takes 5.28 years to complete one circuit. That orbit is inclined about 58 degrees to the plane of the planets. Such a steep inclination is unusual for any short-period comet, and its perihelion, meaning its closest approach to the Sun, is extraordinary. It passes within 0.124 astronomical units of the star. That distance is about 27 solar radii from the surface. It is the smallest perihelion distance of any numbered short-period comet known. Picture that orbit for a moment against something more familiar. Every 5.28 years, a 6-kilometer comet dives inside Mercury's orbit. It skims the outer corona of the Sun and then climbs back out. That orbit alone would make the object interesting enough already. Then there is the chemistry of it, which is stranger still. Spectroscopic observations found the object to be severely depleted in cyanogen. It is also depleted in carbon chain molecules relative to essentially every comet measured. Multiple independent studies have documented that composition over the years. The depletion is severe enough that researchers have raised an uncomfortable possibility. The object may have formed somewhere very unusual within our solar system. Or it may not be native to this solar system at all. That question has never been settled, and it may never be. And the object is not alone out there, which is the final piece. It appears to be the largest surviving fragment of something much larger. That progenitor broke apart, and its debris now spreads across many orbits. Researchers have given that resulting family a name, the Mach-Holes complex. That complex links the comet itself to the Marsden and Cracked Sungrazer groups. It links to an asteroid designated 2003 EH1. And it links to a whole set of meteor showers we see annually. Those showers include the quadrantids in January, the daytime areatids, and both Delta Aquariid streams. One object shattered, and its pieces now intersect our orbit at several points yearly. The Alpha Capricornids have their own story, and it contains a remarkable date. Their parent is a comet designated 169P Neat. Modelling by Peter Jenniskens and Jeremy Vaubayon reconstructed its history. That parent appears to have broken up 3,500 to 5,000 years ago. The resulting stream carries a total mass around 90 trillion kilograms. Most of that mass is not currently crossing Earth's orbit at all. But it will be, and the modelling gives a window. Their conclusion is that this shower becomes a major annual event later. The window runs roughly from the year 2220 to the year 2420. In that period it will be stronger than any annual shower we currently have. It will not be a single spectacular night of meteors either. It will be a permanently stronger shower, arriving every July for centuries. So the handful of fireballs you might catch through moonlight this week matter. They are the leading edge of something spectacular for people not yet born. There is one last convergence worth naming before we leave the sky. Meteors ablate between roughly 80 and 120 kilometers altitude. Aurora is produced by particles precipitating from 80 kilometers up through 300. Those ranges overlap almost exactly, as noted earlier with the colours. If Aurora reaches your latitude and a fireball crosses it, both occupy the same air. Do the two phenomena interact with each other in any way? Essentially they do not, and the energy densities are not remotely comparable. Meteor trails can affect radio propagation, and meteoric metals do influence the ionosphere, but a meteor does not make aurora, and aurora does not make meteors. They are unrelated processes that happen to share an altitude band and a date. and that is exactly what makes the 30th of July worth marking down. Comet debris from an object orbiting every 5.28 years. Plasma from a star running on an 11-year magnetic rhythm, both arriving at the same place on the same night, on schedules set long ago, neither of them caring in the slightest whether anybody happens to be watching. Track that indifference with me, because the historical record is built from it, and the record contains one night that makes everything tonight look modest. Part 16. The record of what this star has already done. On the morning of the 1st of September, 1859, an English amateur was working. His name was Richard Carrington, and he had a private observatory at Redhill. He was projecting an image of the sun onto a screen and sketching sunspots. That was his daily routine, performed carefully for years on end. At about 18 minutes past 11, two patches of intense white light appeared. They appeared inside the sunspot group he had been drawing that morning. Carrington assumed at once that something of his had broken. He suspected a fault in his equipment, or a cloud, or his own eyes. He ran to fetch a witness who could confirm what he saw. By the time he returned, the two patches had already faded away. He had just become the first human being to observe a solar flare. Independently, another English observer named Richard Hodgson saw precisely the same thing. Two men, in two places, watching the same event without knowing it. What made it visible in white light tells you how energetic it was. It stood out against the blinding disk of the sun itself. Flares visible in ordinary white light remain rare even today. A coronal mass ejection accompanied that flare, and it came directly at Earth. It crossed the distance in about 17.6 hours. Hold that number up against everything already established earlier tonight. An average transit takes 2 to 3 days from launch to arrival. A genuinely fast event takes under a day, which is already exceptional. 17.6 hours places it among the fastest transits ever measured, and it was almost certainly cleared by an earlier ejection sweeping the path. The same mechanism described with the two waves in the channel. What followed was the most intense geomagnetic storm in the observational record. Aurora appeared at latitudes where Aurora simply does not belong. They were seen from Cuba, from Hawaii, from Colombia, and from Chile. Reports place sightings down to about 18 degrees geomagnetic latitude near Panama. In the northeastern United States, accounts describe light bright enough to read by. People rose in the night believing that morning had arrived early. And the telegraph network failed in ways that were, at the time, incomprehensible. That network was the only continent-scale electrical infrastructure then in existence. It was, in effect, the first accidental antenna ever built. Operators received electric shocks directly from their own telegraph equipment. Telegraph paper caught fire in some offices, and pylons sparked along the lines. And on some circuits, operators disconnected their batteries entirely and kept working. The induced current in the wire was sufficient to carry the message alone. I want you to sit with that last detail properly. The storm was, briefly, powering the telegraph network by itself. The infrastructure of that era did not merely fail under the strain. It was taken over and driven by the very thing that broke it. The intensity of that event is still debated among researchers today. Early estimates put the minimum Ds near -1,760 nanotesla. Later analysis revised that substantially downward to around -900. The uncertainty band on that revision runs from about -750 to -1050. Either figure sits far beyond anything measured in the modern instrumental era. Now, 1859 does not stand alone in the record. Let me run through the others, because the pattern across them is the argument. May of 1921 produced what became known as the New York Railroad storm. Analysis suggests an intensity broadly comparable to the event of 1859. Telegraph and railroad signalling failed across the northeastern United States and Europe. A railway signal tower at 57th Street in New York burned. The world of 1921 carried vastly more electrical infrastructure than 1859. It carried only a small fraction of what exists across the world today. May of 1967 produced an event with a very different character. This next one nearly ended somewhere far worse than a blackout. A solar radio burst jammed the radars of the American ballistic missile warning system. Multiple early warning radars went blind at essentially the same moment. In the political climate of 1967, that reading had one obvious interpretation. Simultaneous jamming of early warning radar is consistent with preparation for attack. Forces were readied accordingly while the true cause remained completely unknown. Solar forecasters, working in a military service then only a few years old, identified the source. They established that the sun had caused it, and they did so in time. Dolores Knipp and colleagues documented the history decades afterward from declassified material. August of 1972 brought the storm I mentioned earlier. United States Navy sea mines were seeded in the waters off Hon La, Vietnam. Those were magnetic influence mines, designed to detonate when a steel hull passed. Roughly 24 of them detonated spontaneously, with no ship anywhere near. Declassified naval analysis concluded there was a high probability the storm triggered them. A geomagnetic disturbance produced exactly the magnetic signature those mines were built to detect. That is the same event that fell between Apollo 16 and Apollo 17. October and November of 2003 brought the Halloween storms. Those included a flare rated X17 and another estimated near X28. The second one saturated the instruments attempting to measure it. We know for certain that it was enormous in size. We do not know exactly how enormous, because the detectors ran out of scale. I have already described what that event did to satellites and to Sweden. And then there is the one that did not happen at all. On the 23rd of July 2012, an extremely fast ejection crossed Earth's orbital path. It was measured directly, in full detail, by the Stereo A spacecraft. That spacecraft happened to be sitting exactly where the cloud went through. Estimates of its intensity, had it struck Earth, reach around minus 1,200 nanotesla. That places it in the territory of 1859, or beyond it. Earth had passed through that point in its orbit roughly a week earlier. Daniel Baker of the University of Colorado led the analysis of that event. He said that in his view, the storm was at least as strong as Carrington. He said that the only real difference was that it missed us. He also said that if it had hit, we would still be picking up the pieces. That statement was made in 2014, 2 years after the event. He was describing the condition we would still have been in at that point. Keep that near miss in mind, because it sets up the only number that matters. So how often does an event like this actually happen? Pete Riley of Predictive Science published an analysis in the journal Space Weather. That paper appeared in 2012, the same year as the near miss. He examined the statistical distribution of extreme events and extrapolated the tail. His estimate was that a Carrington-class event had a 12% probability. That probability applied to the following decade based on a defined intensity threshold. 12% per decade from the best analysis available at the time. That number has been debated extensively in the years since its publication. Later analyses have produced both higher and lower figures than his. The result depends heavily on the dataset used and the fitting method chosen. I am not presenting 12% as settled fact because it is not. I am presenting it as the number that has anchored a decade of policy discussion. And I want to translate it, because probabilities in that range are badly intuited. 12% per decade means the cumulative probability climbs steeply over a lifetime. Across 50 years, the cumulative figure approaches roughly 1 in 2. A child born today has better than even odds of living through one. Now compare that against how you treat other risks at similar probability. If somebody told you an aircraft carried a 12% chance of crashing, nobody would board it. That airline would not still exist by the following morning. And yet 12% per decade for an event with a multi-year recovery gets treated differently. Across most of the economy, it is treated as a risk not worth planning around. That gap between how we price the two risks is the real subject here. One more comparison belongs here, because it puts the scale in perspective. On the 15th of February 2013, an object entered the atmosphere over Russia. It exploded above the city of Chelyabinsk in the morning sky. The airburst injured roughly 1,500 people across the region. Almost all of those injuries came from glass, blown inward by the shockwave. The energy released was equivalent to about 30 Hiroshima bombs. Nobody saw the object coming, because it approached from the direction of the sun. I raise that event here for one specific reason tonight. It is the most recent occasion when something from space injured people directly, and the entire world had roughly 0 seconds of warning before it happened. Space weather at least gives us minutes, and sometimes days of estimate, but the comparison runs the other way as well, and it is instructive. An airburst over one city injures thousands and breaks windows across a region. A severe geomagnetic storm injures nobody directly, anywhere, at any point. It simply removes capabilities that entire economies now assume are permanent. Those two hazards sit at opposite ends of a spectrum. One is violent, local, visible, and immediately understood by everybody. The other is silent, global, invisible, and understood by almost nobody. Weigh carefully which one your society is actually prepared for. Considerable effort now goes into finding objects like the Chelyabinsk impactor. Survey telescopes scan the sky nightly, cataloguing near-Earth objects continuously. The catalogue grows every year, and the risk is genuinely being reduced. That work is funded because the hazard is easy to picture. The equivalent effort for the invisible hazard is far smaller. It amounts to a handful of spacecraft and a few hundred specialists worldwide, and the invisible hazard is the one with the 12% decade. Which brings us back, finally, to this week and to Thursday. The storm arriving on the 30th of July is not that event. It is a watch at level 3, issued by careful people using good models. It is an ordinary occurrence for an active star in a declining phase. Most likely it produces Aurora, some radio degradation, and some navigation error. It will be nothing that anybody remembers by the middle of August. I want that stated plainly, because frightening you about the wrong thing serves nobody. But hold this next point, because it is where the whole argument lands. Every single event I have just described began in exactly the same way. A numbered region appears on the disk and is catalogued. A flare is recorded and rated by the monitoring satellites. An ejection is observed leaving the corona a short time afterward. A model is run and produces an estimated arrival time. A watch is issued, in careful language, describing a range, though nobody had the vocabulary to say so. 1989 began that way, with a flare recorded on the 6th of March. 2024 began that way, with a large region rotating into view. The announcement itself looks identical every single time, without any exception. The difference between an ordinary week and 1859 is not in the announcement. It is not in the model output, and it is not in the language used. It is in the orientation of a magnetic field inside a cloud, and that orientation cannot be measured until the cloud is 15 minutes away, which means the honest position tonight is uncomfortable but simple. Nobody is hiding anything from you, and nobody knows what happens on Thursday. The instrument that will know first is sitting 1.5 million kilometers upstream. It has been fully operational for less than 2 months, and the door it watches for is either latched or standing open. Part 17. The thing you will not be able to see. So what actually happens on Thursday? And how would you know? The likely outcome is the quiet one, and it deserves stating first. The merged cloud arrives with its field pointing mostly northward, or only briefly southward. Conditions reach level 1 or level 2, and the Aurora stays north. Radio degrades at high latitude, navigation slips briefly, and the drag rises slightly. By Sunday the whole thing is over and largely forgotten. The less likely outcome is that the merged field points south and stays there. Then the oval expands, the errors grow, and the operators start working. Watch for it yourself rather than taking anybody else's word for it. The 3-day forecast gives the predicted index in 3-hour blocks. The Aurora viewline shows how far south the oval is expected to reach, and the real-time solar wind display carries the raw feed from that buoy. That last one is the one that matters on the night. When the cloud arrives, you will see the shock first. Speed jumps, density jumps, and the total field strength jumps with them. Then watch the north to south component, and watch only that. If it drops sharply negative and stays there, the storm builds over hours. If it hovers near zero or turns positive, the door stays latched. You will be reading exactly what the forecasters read at the same moment. There is no privileged information available anywhere in this entire field. There is the instrument, and there is what the instrument sees. Which returns me to where we started tonight, and to the question itself. Which way is the magnetic field inside that merged cloud pointing? Nobody can answer that yet, and the answer will arrive 15 minutes ahead of the storm. That is not a failure of anyone's competence or funding. It is the geometry of standing directly in the line of fire, and the ratio underneath it has not changed all evening. 15 minutes of warning against machines that take up to 5 years to replace. On the night of the 30th, a moon at 98% will flood the sky. 2 meteor showers will peak beneath it and be almost entirely erased. Debris from a comet that dives inside Mercury's orbit every 5.28 years. And a cloud of solar plasma arrives on that same night from the usual direction. You will not see the part of this that actually matters. You did not see it in 2022 when 38 satellites came down. You did not see it in 2024 while tractors stood still across the Midwest. The visible thing and the consequential thing were the same event both times. The attention went entirely to the half that could not hurt anybody. So the sky on Thursday will be full of things nobody can see. Some of them are fragments of a comet that shattered thousands of years ago. One of them is the magnetic field of a star arriving on schedule. And only one of those has ever reached through the atmosphere to touch the ground. The star is not finished with this cycle, and the declining phase runs into 2027. The regions now rotating away will come back around in about 27 days. The next watch will read almost exactly like this one did,